All right. Balanced chemical equations for acid-base reaction. Got an example of that right there on the board. Identify a substance acting as an acid or a base in a given reaction. Right? From last year, acids are proton donators, bases are? Proton receivers. Thank you. Explain the reasons for the selection of a particular acid-base indicator. We've talked about indicators, haven't we? And that relates to pH curves. Where is the equivalence point? Identify that. The middle of where that sharp drop is. Read off roughly where that pH is. Select the appropriate indicator. Perform stoichiometric calculations for volumetric analysis in acid-base titrations. Already gone through an example. Okay, so recap from last year. Lowry-Bronsted, as we said, proton donator, proton acceptor. Amphiprotic, substance can accept or donate a proton. Monoprotic, diprotic, acids, right? Mono means, di means dead. Tri means 3. What's an example of a triprotic acid? Phosphoric. There we go. Fantastic. Conjugate acid-base pairs, and I've mentioned that in reference to titrations. Suitable indicator for this was phenolphthalein. Why? This is slightly basic. So the equivalence point, right? Weak acid, reasonably strong conjugate base. Basic is the neutralized solution. Yeah? Or we're adding also, another way to think about it is we're adding a base to neutralize the acid. We're looking for the point at which it becomes slightly basic, because then that's the point at which NaOH is in excess. Right? Hence, use that base indicator. Different reaction types. Main ones are our 4. Acid and metal gives us salt and hydrogen gas. Don't really need to worry about that. That's actually a redox reaction. Acid plus a hydroxide or oxide gives us salt and water. Acid plus a carbonate gives us salt, carbon dioxide, and water. Remember, strength and concentration are not the same thing. Strength is the readiness of giving off a proton or accepting. Concentration is how much you have. Concentration, weak acid. Yeah, concentrated, but weak acid, for example. My way of thinking about it is strength is readiness. Concentration is the quantity of the substance. I know, does that just break your mind? Yeah. Remember, using weak acids, we use the equilibrium arrow. It's not that important because we don't do the equilibrium of acid and bases in this course. pH, don't need to worry too much about pH. Yeah? Don't need to worry too much about pH. Don't need to worry too much about this.
Will pH calculations
No. It may pop up on your exam. May.
If the solution's at 100 degrees, the
pH goes down. Right? And the reason, quick reason for that is the self-ionization of water is endothermic. What do we know when we increase the temperature of an endothermic system? Drives the reaction forward, right? So the concentration of H3O plus increases, as does the concentration of OH minus, but pH is a measure of H3O plus. Yeah? Okay, here we go. Interesting that in this, I might well, let's skip this question. Yeah, I'll skip this one. It's not a direct titration. But what I want to highlight with this question is you might get a question like this on an exam, right? It is a stoichiometric problem, yeah, but it includes gas laws. So that idea of combining areas of study together. Anyway. Don't worry about first and second ionizations. I'll move forward. I'll go to this instead. BCAA question 2009. A student accurately determines the concentration of a solution of sodium hydrogen carbonate, or bicarbonate as it's also called, in a titration against standard solution of hydrochloric acid, HCl. What's a standard solution? Thank you. word for word. Is HCl a primary standard? No. So we would standardize it against a primary standard. Yeah? Cool. First step in this experiment is to accurately dilute 100 ml of a 1 molar HCl stock solution to 0.1 molar using a 1 litre volumetric flask. So we're diluting by a factor of 10. However, instead of using distilled water in the dilution, the student mistakenly adds 900 ml of 0.0222 moles of sodium hydroxide. Stupid student. That's what they did, okay? All right, so write an equation for the reaction that occurs in the 1 litre volumetric flask. So HCl plus NaOH gives you what? NaCl and water. Excellent. Calculate the concentration of the hydrochloric acid in the 1 litre volumetric flask after the student adds the sodium hydroxide solution. How would you go about doing that? Right. Well, we've got 100 ml of HCl, of 1 molar HCl, yeah? So let's pause that and have a go. Student then uses this contaminated HCl to determine the accurate concentration of the unknown sodium hydrocarbonate solution. Will the calculated concentration of the sodium hydrogen carbonate solution be greater than, smaller than the true value? All right, hands up if you say greater than. You've got a 33% chance of getting it right. Oh, actually, 50%. You only got choice, greater or smaller. Who says greater? Who says smaller? You say greater? You're correct, but why? Right, so you're diluting the acid, so the titer will be more, which gives you an apparently higher concentration of your analyte. Yeah? There we go. Do, 36%. Only 36% got that right. And what do we have? 2 of you in the room that got that right. Yeah? Application. Think. Work through the process. If I dilute what's in the burette, what effect will that have? This is all our rinsing errors that we've discussed as well. Yeah? If we have extra water in the burette, dilutes what's in the burette, titer must be higher to neutralize what's in my conical flask. If that's higher, what's in there gives me apparent higher concentration. If I were to rinse my conical flask with the acid, then that neutralizes some of what's already in there. Titer becomes smaller, concentration of this becomes lower. Yeah? So think about that. Redox titrations. Describe appropriate procedures for volumetric analysis that involve redox titrations of some common consumer products. Perform stoichiometric calculations for redox titrations. Right. Quick recap of redox. Yeah. Oxidation, oil, rig. Involves loss of electrons, reduction involves gain. Transfer of electrons occurs. Oxidizing agent causes oxidation, undergoes reduction. Reducing agent causes reduction, undergoes oxidation. Yeah? Oxidation number, not going to worry about that too much, but cohes. Remember, cohes is only in acidic solutions. One example of a redox titration is the determination of ethanol in wine, in which we might use iron solution or potassium dichromate. What's dichromate? What do we know about that? It is orange. It's an oxidizer. So what's going to happen to the ethanol in the wine? And what's happening with the dichromate? It's going to reduce to chromate ions. Yeah? So and at the end point, or the equivalence point, is when we see that color change. We saw that in the previous 2 weeks ago. Yeah? Remember how it went from orange to green? And at the point at which it goes green, it will stay orange, stay orange, stay orange, go green once we reach excess. Yeah? Yeah. Once all of that ethanol has been oxidized, we see that color change. Do we need an indicator? No. Why? It's self-indicating. Yeah? Self-indicating reaction. We could use also permanganate, and that goes from a purpley to a colorless solution. Iodine goes from browny purple to colorless as well. And that's what we're going to be doing on Thursday, looking at the vitamin C content. Cool. Straight into an exam question. Okay. What I'm going to do, I'm going to read this really, I'm going to pause so I can read through the first bit. Ratio between iodine and water in this reaction. 2 to 1, right? Mole ratio we need. So iodine to water is 1 to 1. Excellent. Iodine titrating agent was prepared by dissolving 15 grams of iodine in methanol using a volumetric flask, made up to 500 mils. 10 ml sample of oil was analysed. Using the iodine solution, the mean titer was found to be 4.95 mil. Jacob, thank you. Determine the mass of water present in the 10 ml sample of oil. All right, let's break this down. Okay. First one, 1 to 1, 88%. Nicely done. Most incorrect response was 2 to 1, which is the ratio of iodine atoms to water molecules. So looking at the wrong sides of the equation. Question 8C, only 26% got 2 marks. Yeah? But notice how there's 4 things to calculate for those 2 marks. 1 mark awarded for accurate calculation of N of I2 in the titer. So all the way down to here, just to get your first mark, and then your second mark to convert that, because it's the same, to mass of water. Most students struggle to effectively interpret and use the data provided. Most worked out the N of I2 in 500 ml solution here. Many did not then proceed to work out N of I2 in the titer. The fact that water was in the analyte may have confused some students. 34% got 2 marks in the second part. Density of oil, using the mass from before, 1.14. Many students were unable to link together the required data, volume of oil, density of oil, and mass of water in the oil sample to arrive at the percentage of mass on mass of the water in the oil. Students should be aware that determining the percentage by mass requires the mass of the ingredient and the mass of the sample. The inclusion of the density of the oil should have been an indication that the relationship D equals M on V could be used to determine the mass of the oil. That's it.